All right, welcome back to this lecture series. So we'll start with our lecture number 2. And lecture, you can see the lecture list here. So we covered number 1 already. Today we are going to cover the resistive sensor materials and its fundamentals. So I start with key references that you can follow for additional reading and some supplemental reading as well. So ceramic-based resistive sensors can be categorized into 3 groups. One is the so-called bulk conduction based, which are supposed to be dense material of your ceramic. So you can make sensor out of many of these oxides. Then one can make so-called metal oxide junction based. So the sensor will be basically where there is a contact interface between metal and oxide. And examples are the Schottky diode type, or the metal oxide semiconductor, or the metal insulator semiconductor on a field effect transistor platform type. And the last group that I will spend most of my time is the surface or intergranular controlled, which as opposed to the bulk type, which is dense, this is going to be porous type materials. And you can make those out of, again, tin dioxide, TiO2, and other oxides. So starting with the bulk type, in general, for any oxide, electrical conductivity can depend on the temperature-dependent part, and there is a part contribution to the conductivity that depends on the oxygen partial pressure. And if you do Kroger-Vink type analysis of point defects in oxide materials, you can actually show that conductivity can depend on oxygen content as integer type slopes, so negative or positive of 1/n, where n is typically an integer. And again, I'm not going to go into the discussion of Kroger-Vink type diagram, but if you're interested, we can do that later. So you can look at, so this is some data based on barium titanate material and electrical conductivity as a function of oxygen partial pressure. You can see that the material goes from N-type semiconductor to P-type semiconductor. And particularly in the N-type regime, the slope, this 1/n, can vary. At low temperature, typically it's 1/4, and change to 1/6 at high temperature. And that has to do with whether doubly ionized oxygen vacancy that you create at high temperature compared to singly ionized oxygen vacancy that you create at low temperature. So these are the bulk types. So the idea is that you measure the electrical conductivity, and from the conductivity, you can figure out the gas environment. So for example, if you're trying to detect CO using one of this bulk type sensor, you can measure the conductivity of the sensor, and from the calibration curve, you can figure out the PO2, and the PO2 concentration will be related to the carbon monoxide, for example, meaning that as you increase carbon monoxide in the environment, you'll be decreasing PO2. The second type, which are the junction-based type, you can make it in many forms. One is the so-called capacitive mode. So you can make a capacitor on a metal, you can take a semiconducting material, put a thin insulating layer with a metal gate, and then you can measure the capacitance versus applied voltage to the metal gate. And then, depending on the gas that absorbs at this interface, there will be shift in the capacitance voltage curve, CV curve, and particularly for reducing gases, they will shift to the left, and for oxidizing gases, it will shift to the right. So depending on the amount of the shift in the CV, you can actually create a calibration curve for gas concentration. Or you can make it in this Schottky diode type mode, where you again put an insulating layer with a metal gate, and you can measure the IV, and the IV will be nonlinear. And depending on the gas absorption or the type of gas absorbed on this interface, the IV curve will shift either to the left or to the right, because by absorbing gas molecule, you'll be modulating the height of the Schottky barrier. So, or you can make it in PN junction mode. So with a semiconductor, put a different semiconductor by doping with a metal gate, and then you can basically modulate the PN barrier by absorbing gas on this at this interface. And that will also give you this shift in the IV. Or you can put this insulating layer on a field effect transistor with a source and a drain. And depending on the applied voltage to the metal gate, you can modulate the current flowing through the insulating layer. And that will give you a nonlinear IV again. And that IV can be either shifted to the left or to the right, depending on the type of the gas that absorbs from this interfaces. So you can see that compared to the bulk sensor, this interfacial or junction type sensor is basically, the junction is this using as the sensing element, and the rest is basically a holder for that junction. And here are some examples of how you make a Schottky barrier that depends on the Fermi energy level of the metal or work function of the metal that you put on the semiconductor. And if the work function of the metal is lower than the work function in the oxide, then you get this electron transferred from the oxide to the metal, and that gives a bending upward, and that you create a Schottky barrier at the metal semiconductor interface that gives you a nonlinear IV curve. And the other hand, if you're trying to do electrical measurement, you have to make ohmic contact, and ohmic contact is created by reverse. So in that case, Fermi energy level of the metal would be higher level of the work function, I should say. Sorry about that. Work function in the metal has to be at a higher level than work function in the semiconductor. In that case, you will get a band bending downward. That is a downhill motion. So there is no barrier at the metal semiconductor interface. And that will give you linear behavior for an ohmic type measurement. So for sensing, you make a Schottky contact. And here is an example. You can take your oxide, either tin dioxide or titanium dioxide bulk. On one side, you make ohmic contact, and you can make ohmic contact by putting metal like silver or gold. And on the other side, you can make Schottky contact. So you can use palladium on tin dioxide or platinum on titanium dioxide that will make Schottky contact. And again, the idea is that you're going to measure IV, and from the shift of the IV, for example, IV on a contact like this in air will look something like this. And then as you add carbon monoxide, for example, you will be lowering the PO2 in the environment. And the IV, you can see as you decrease the content of oxygen or increase the content of CO, you can see you're shifting that IV curve to the left. And from the amount of shift, you can relate that to the amount of gas concentration. The other type from the junction-based is the metal oxide semiconductor or metal insulator semiconductor and field effect transistor platform. So if you look at the kind of mechanistic approach, so if you're using a sensor based on silicon semiconductor with a insulating silicon dioxide layer, and a palladium metal on top of it. And then if you're using this in an environment of oxygen, hydrogen, and H2O, then your hydrogen actually will absorb on the palladium, dissociate into atomic hydrogen, and will diffuse through the thin palladium layer, come to this interface and make this so-called dipole. And this dipole will actually change the Schottky barrier at this interface. And you can do the measurement on a device like this, either in the CV, capacitance voltage mode, on a construction like this, or on an FET platform with a semiconductor, with an insulator, with a metal gate. And again, from the shift of the IV, you can figure out the concentration of the gas. So that's the junction-based type sensing that people do. And the next one that I'm going to talk about, the intergranular type or surface controlled sensor that you make by depositing a coating of the material on top of a interdigitated electrode printed on an alumina substrate platform. And then you put your sensor in this environment or in a furnace where you can do the measurement both as a function of temperature and gas concentration by flowing gas from gas cylinders. And in the actual device or actual measuring setup looks something like this. So this is your furnace in which you have a quartz tube, and your sensor is going to sit inside that quartz tube in the middle of the furnace, and you can flow gas by controlling by mass flow controller into the furnace and use a multimeter DAC system to collect data that will allow you to calculate change in resistance as a function of both temperature as well as gas concentration. And the DAC system is connected to a desktop that can automatically collect the data. So let's talk about the intergranular contact type. So you have a substrate where you can have bottom electrodes, electrode printed on top of the substrate, and you put your coating. So this is my coating of the oxide. Or you can use side electrode, or you can use top electrode. So basically in your coating, you have this particle-particle contact. So I'm going to show this, one of this interparticle contact. So you have this oxide particle to the left. What happens is from the ambient, oxygen will absorb, chemisorb actually on the surface of that particle. And because of the Fermi energy level, which is lower in the absorbed oxygen compared to the oxide, so electron will be extracted from the near surface area of the oxide to create an electron depletion layer near the surface. And that will lead to the band bending as you approach from the bulk to the interface of the particle. The band will bend upward because of electron extraction. You'll have similar scenario to the particle to the left. So I'm actually showing you one of this interparticle contact here. So create this back-to-back Schottky defect or Schottky barrier, I should rather say, that will lead to the high resistance of the material to begin with. And the resistance for the conductivity of the material is determined by the barrier height at this interparticle contact. Now, if you expose this coating to a target gas, like carbon monoxide will come and interact with the surface absorbed oxygen, and it will actually create CO2 that will dissolve. And in the process, it will donate an electron back to this oxide. Hence, if it's an N-type material to begin with, the donation of electron by reacting with gas molecule will lead to the drop in the resistance of the material, and it will also make this a depletion layer width thinner and thinner as you react more and more of the target gas. The scenario will change if you go, so this is the N-type material. Again, you can see this depletion layer depletion layer back-to-back Schottky barrier, and conduction is through the bulk part as well as across the interface, and resistance is controlled by the interface. On the other hand, if it's a P-type material, it will create actually oxygen absorption, will create a surface accumulation layer, accumulation of electron, and your conduction will be through the surface layer. So actually in this case, as you react your target gas, like CO, the resistance will actually go up. Okay, so in N-type it's reverse, and in P-type it's just the opposite. So a typical response from a sensor like this will be that you equilibrate the sensor in the background gas. This can be air or nitrogen or something like that. Then you introduce CO, and the resistance will drop. It's an N-type material. And one takes the 90% response, because beyond 90%, the change is very slow. And then once you cut off CO, the sensor should recover completely to the previous state. And this is the beauty of this type of sensor, because the target gas is not interacting with the material, but it's interacting with the surface absorbed oxygen on the surface of the material. And you can define response time, 90% response time. How long does it take for the signal to drop to 90%, and 90% recovery time? How long does it take to recover 90% of the original signal? And you can see that response is fast, but recovery is sluggish. And there's a reason for that. Remember, when you stop CO, the electron that was injected by reacting with CO has to come back all the way to the surface for desorption, or for reversing the reaction. And there is some delay in conduction of that electron back to the surface. That's why recovery is typically sluggish. So you create a calibration curve by taking this 90% response. So let's say this is 100 ppm of CO. You take 90% response, and you're going to create a calibration curve where you're going to show that 90% resistance value as a function of 100 ppm. And then you introduce 500 ppm and take the 90% response again and plot that on that response versus CO concentration. So you create a calibration curve where you'll see the response as a function of CO concentration will keep on going down, and eventually it will saturate at some level. And it will saturate, as you can imagine, at the level when all of this absorbed oxygen is reacted by CO. So when all of these are reacted, even we increase CO concentration, the sensor response will not change anymore. So it will saturate at some concentration of CO. Just a little bit about the chemisorption and physisorption. So if you take a Leonard-Jones model of physisorption and chemisorption, you typically, the gas molecule, so this is your oxide surface. Your oxide material is to the left, this is the surface. As you bring gas molecule closer to the surface at some point, at some distance from the surface, it will physisorb. The molecule will create some sort of van der Waals type interaction with the surface. And the physisorption activation barrier is not very large. It's about 5 kilocalorie per mole. On the other hand, chemisorption, interaction between the gas molecule and the surface involves electron exchange. And it's stronger interaction compared to physisorption. So you can chemisorb, for example, and you can probably dissociate with, provided the energy, large energy of dissociation, you can dissociate into atomic oxygen or whatever the gas is. And then the dissociated molecule, as you bring it up closer to the surface, it actually chemisorbs at a distance RC, but you can see the chemisorption energy is large, about 5 times larger than physisorption. And so it's about 25 kilocalorie per mole. Typically, chemisorption doesn't happen through dissociation process because it requires a large amount of energy. So what it does is it physisorbs first, and then with raising the temperature, you can overcome the activation barrier for chemisorption, and then at high temperature, it chemisorbs. So typically at low temperature, you deal with physisorption, and with a little bit elevated temperature, you deal with chemisorption. So the sensing that we are talking about, this O- that you create, is a chemisorption process of oxygen on the surface of the oxide. And if you look at the coverage, the coverage versus temperature curve, you can see that at low temperature you have physisorption. Then it increase in temperature, there is a transition from physisorption to chemisorption. And then if you go to high temperature, even the chemisorbed species will start dissolving. So the coverage will go down. So what happens is you will see that this sigmoidal type behavior will be followed in conduction behavior of the material. So at low temperature, it will be dominated by physisorbed species. Chemisorbed species will take over. Chemisorption will increase, and so will the sensitivity of the material. The sensitivity will maximize somewhere there. And then beyond that temperature, desorption will take over, and the sensitivity will go down. So that's the, let's take an example of absorption of various molecules on surface of tin dioxide. You're looking at coverage again of this type of species on the surface as a function of temperature. So you can see that at low temperature, physisorption of water dominates. That goes down as you raise temperature. And then OH chemisorption takes over, and oxygen chemisorption. That also will go down. Both of them will go down as you go to high temperature because of desorption of these molecules. And even the electrical conductivity of the material or resistance of the material actually mimics this very well, the absorption behavior. And you know that the absorption of these different types of species will affect resistance in different ways. So oxygen absorption will raise the resistance, so will OH absorption, but water molecule absorption will actually decrease the resistance. So, you can see the decrease of resistance here, dominated by absorption of water, and then this increase in resistance dominated by this species. But then when you go beyond that temperature, this species will start dissolving, and the resistance will follow the same behavior. So, the conduction behavior of the material mimics the gas absorption of the surface very well. So there is always a question of, do we have molecular oxygen or atomic oxygen absorbed on the surface of the oxide? So you can do different types of measurement, electron paramagnetic resonance measurement, temperature, program desorption measurement, and so on. And you can actually detect a species, and you can see at low temperature, molecular oxygen dominates. Intermediate temperature, atomic oxygen dominates. And then if you go to higher and higher temperature, you can get oxygen absorbed with 2 electron extraction. Okay, or even at very high temperature, you may see involvement of lattice oxygen in the absorption process. And what is species dominant and how much will depend on both the temperature as well as oxygen content in the environment. And people play this game of controlling those variables by changing both the temperature and PO2. Let me talk a little bit about what happens if you take large particle versus nanoparticle to make your sensor. So if you use particles larger than the depletion layer width, which is typically tens of nanometer depletion layer, you will have this bulk versus depletion layer and back-to-back Schottky barrier that we talked about. And then as you introduce it to the target gas, then this depletion layer width decreases and you get conductance, change in conductance or change in resistance through this height of the Schottky barrier. So for large particle, the sensing is controlled by the magnitude of the Schottky barrier. On the other hand, if you use nanoparticles, if the particle size is particularly less than the width of the depletion layer, in that case, the particles will be completely depleted. There is no more bulk left anymore, undepleted region. And then the material, the coating conductance, will be controlled by the flat band condition. In the flat band condition, the sensing will be controlled by the modulation or change in the Fermi energy level with respect to the conduction band energy level. So as you absorb gas, this EC minus EF will change because of the electron density in the conduction band. So the mechanism for the large size particle versus nano size particle is completely different. From a sensing point of view, you will get bigger response, bigger drop in resistance in this type versus here. But in terms of range in sensitivity, remember, the nanoparticle will give you larger surface area that will allow absorption of more oxygen that will be available for the reaction of CO. With this sensor, you will be able to increase the range of sensitivity, but these type will give you higher sensitivity because you can get bigger drop in resistance compared to this case. Let's talk about selectivity of the sensors, which is an important concept. The selectivity can be obtained by fixing the operation temperature at the maximum sensitivity temperature. So for example, this is on a tin dioxide material. You can see hydrogen sensitivity maximizes at around 150 degrees C or so, whereas methane, hydrocarbon, methane, and so on has shifted. So if I use one of the sensors and operate at this temperature, exactly at this temperature, my sensor is going to get most of the signal from hydrogen, and the interfering gas signals will be very, very minimal, practically none at that temperature. So that's one way of making selective sensor, by fixing the operation temperature. The other way is the chemistry way, that one can use selective catalyst to chemisorb particular molecule compared to the other. Or you can use a selective membrane. You can put a membrane layer on top of your sensor coating with controlled porosity that will allow certain gases to pass through and will filter out all the interfering gases. That's another way of making selective sensor. Or you can make N and P type composites. As you remember, for N type material, the reaction with reducing gas will bring the resistance down. For P type material, reversal will happen. So P-type material resistance will bring up by reacting with the reducing gas. So you'll get some compensation. So the game to play here is that by mixing the optimized volume fraction of N versus P phases, you may be able to completely eliminate the effect of one gas, and for other gas, you may be able to get not complete nullification by N-type and P-type conductivity increase and decrease, but you will get dropped sensitivity, reduced sensitivity, but for one gas, you may be able to completely cancel out, but for the other gas, you don't cancel out. So that is another idea of making selective sensor. But in many real applications like automotive exhaust, with so many gases, in automotive exhaust, you have hydrogen, water vapor, CO, CO2, NOx, at least 10 different hydrocarbon and so on. So even you design a very selective sensor, that selective sensor will not be selective after all in an automotive exhaust. So what do you do in this kind of application? You actually design a sensor array, multiple sensors with different degrees of interference. And then you can use a well-trained software like LDA or neural net type or principal component analysis type software that is well-trained, trained by collecting data in the lab. And then if you have a well-trained neural net, you can use sensor array to find out gas composition in an unknown environment. Let me talk about sensor design and electrode structure. So here is your substrate, and you are going to put a sensing layer on top of it. So you can use the top electrode. So you put your electrode on top of the sensing layer, or you can print the sensing layer on an electrode printed substrate. So that would be called bottom electrode, or you can put the electrode on the side of the film, side of your sensor film, side electrode. And also electrode can be in different configuration, the so-called interdigitated electrode printed on your substrate, or you can use 4-probe type measurement that 2 of the probes will measure current and the other 2 will measure voltage. Or you can do 2-probe measurement on the top electrode or bottom electrode. There are all kinds of configuration that people use. Particularly the bottom electrode has some advantage of designing selective sensor. So you can actually modulate or control the gap between electrode by controlling the distance between interdigitated fingers, gold fingers on the substrate. So you can control the gap distance as well as you can control the thickness of the layer. And by controlling those, you can actually design selective sensor, particularly if you have a mixture of very highly reactive gases versus slowly reactive gases. So for example, if the gap is small and the thickness is large, what will happen is that your highly reactive gas will quickly react top surface and the signal will never reach the electrode for the signal to pick up the response. On the other hand, the slowly reactive gas will keep on percolating through the thickness of the layer, and this electrode will pick up the signal. So you can modulate the distance versus thickness to design selective sensors. And this is something people do in real life. Looking at the type of oxide that are used for sensing, you can see tin dioxide is the major share. And then other type of oxide, tungsten oxide, titanium oxide. There should be zinc oxide right there, majority. And then other types of oxide and a lot of mixed oxide, where people play with the difference in Fermi energy level of the two oxide that can be designed for selective sensing by pinning the Fermi energy, so-called pinning effect of the Fermi energy level. If you look at the what type of gases these oxides are used for, and again, you can see some of the major one are the carbon monoxide, hydrogen, NOx, and a lot of the other ethanol and CO2. Acetone should be there, ammonia, and so on. So a lot of gases are being detected by this type of oxide-based sensors. With that, I'm almost ready to conclude this lecture. So what are the challenges and opportunities in this area? Obviously, stability is a big topic of research, particularly if we are trying to make high temperature sensor, so-called hostile environment sensor. So there is a lot of materials research and development opportunities. And then sensitivity, obviously one can use nanomaterials and structures to modulate enhanced sensitivity and recovery and response time. Selectivity, you can use add catalyst, membrane sensor arrays, and NP composites type. Response time and recovery time, you can decrease the response and recovery time. One can use submicron and nano size particles. And understanding the mechanism, mechanistic studies and modeling and simulation, there's a lot of opportunities here. And obviously at the manufacturing level, there is a lot of challenges in micro and nano machining, packaging, miniaturization, and so on. This is really a very active area that is a typical material science type work, that you process your material in a certain way, characterize it, control the structure and microstructure, measure the property that has a reflection on the performance. And you can keep on optimizing the processing condition to optimize the crystalline microstructure to give you optimized property with enhanced sensing performance. With that, I'm done, and thank you for listening.